Good morning, everyone. Sorry, you'll probably hear the coffee pot going off in the background here, so I'm waiting for the morning coffee. I'm going to, again, go over some small administrative stuff, and then we're going to look at division. Today is not a horribly long one. In class, this definitely would have been followed up with us doing a worksheet worth of stuff, which I'm going to put up as a quiz online so that you can have questions about polynomial division, because it's going to be important, and we're going to keep doing it, but a lot of today is going to be looking at the different things that happen around polynomial division and doing a lot more examples. I told you you'd hear the coffee pot in the background. I'm hopefully moving into the porch next week to be away from the kitchen noise, but the porch is cold right now. All right, so a couple things to note. Pearson has been having some issues. They seem to peak in the evening, so I'm going to plop over to the web browser here and just show you some things I was looking at. So let's see. Nope, it's not up there. Go back. Firstly, in Pearson, you should be able to see all the assignments now. There is the practice exam, which allows multiple attempts for Chapter 3. The excuse me. The test for Chapter 3. These are both due on the 6th, and the test itself allows 2 attempts. And this was the test we would have taken Thursday last week if we would have been back in class on schedule. So it was due for the Thursday coming through. Then in the homework for the material we're covering today is due the end of next week. I should say the first 3 sections of Chapter 4. And so that is up on Pearson. This practice tests and little Quizlets I'm going to be dropping down. I left a practice test so we would get an idea of how testing worked on Pearson. And I'm allowing 2 attempts on the exam for getting used to it technically. It's not the most, well, if you're used to doing tests on paper, it's not the same. And by not being the same, I wanted to give some room to get used to it. Let me see, that one should be... Alright, what we're going to do here, it's 4 days out. I'm going to, because of the issues with Pearson, I am going to push this out to Thursday of next week. And this is just because Pearson has been having some issues. And I have to do that in both courses. But that's what I wanted to talk about, was Pearson has been booting some things, people out. They've had an extremely large server load. And so they've been having to add more servers. So let me make sure that this. Let me make sure I get all of these put in the right place, and I'll look at push it out to Thursday. All right. And that is there. All right. So there are those due dates come back. Okay. So administratively, that's there. Let me go to Blackboard. And over to course content. So in Blackboard, under course content, there is a link for the YouTube playlist. And what's in the YouTube playlist These individual lectures will be stored. I will try to keep them in order, and I'm going to go back and re-edit the title for the subject going through. And then as I put up example problems are also listed in there, worked out example problems. And so there is a playlist, and the link to the playlist is in the course content on Blackboard, so that we can get back to the videos as need be. So that's what I have administratively. Again, continue to email me questions. I've been trying to create content based on the questions coming across. All right, whoops, that is the wrong thing I wanted to click on. I wanted to click on this. And back. All right, so we're going to continue to look at polynomial division. And in a very, Kiana asked a question, am I familiar with the study plan feature on Pearson? Yes, so I don't assign the side options on Pearson. I particularly initially used Pearson as a way of focusing on specific homework. My goal with it was so that when doing homework, people could get answers immediately. Kind of similar to how answers in the back of the book used to be done, but in a way that they could get answers to the videos or the questions to them as they were working on them. Some of the things the study plan do is okay. I think some of the adaptive features on it, where if you're getting certain things wrong and they re-add it, is nice from a user end, from a configuration end. I prefer the conversation over the machine doing it. I haven't set it up here, and at this point in the course, I'm not going to go back and set it up, but I have had students that have used all the features of Pearson to their additional material. So right now I'm just going to continue to assign homework, quizzes, and exams on Pearson. The quizzes and exams would have been in classwork thing. My pedagogy was to use Pearson for homework only. So I'm adapting it into what I would have used in class. I'm putting on Pearson. I do think in the future I'm going to try to incorporate its features a little bit more. There's pluses and minuses to that. One example is a lot of the stuff we covered at the beginning of 4.1, I also covered at the end of 1.4 and at the end of 2.1. At the end of 2.4, because it talks about functions generally and builds its way up to polynomials. So I've been doing polynomial previews. If you follow their study plan, it doesn't do as much of previewing on that. Or at least I haven't seen a way to do that using the tool. So it's something I'm not going to drop into play right now. I think it would cause more problems than the benefit that would come out of it. But reading the manual for all the different functions on this to see what I am not using has been what I've been doing over the break. And what I've been doing. I also have to use another program called WebAssign for other types of classes, and I'm trying to have a consistency in how I teach between the two, and they're dramatically different, so that if I ever switch textbooks or have to switch textbooks, the material comes out the same. So familiar with, yes, using, probably not at this juncture. But I have always said if things aren't working, I will adapt, because That's what teaching is. We present material. If it doesn't work, you have a conversation with students and you try to find out what's needed. Which is why, these lectures are done in this format, so it can be saved, because I know everyone's schedules are up in the air. The interaction live, I can answer a question like this, and but it can still be stored for people that can't make normal times. All right. On that note, continue to email me questions. I am trying to add examples. I've sent out an email where everything was at. I'm going to continue to do those bulk emails. It looks like Tuesday will be the day that I will bulk email and kind of like a status of where we are. I'm going to be putting as much material into the Blackboard system as I can as references, and leaving a record of everything we do there on out. But if you do have any questions, let me know. Fire me off an email. I try to be 24 hours on my email due to the amount of communication that's come out this way. I'm about 2 days behind in my replies to email. Like if you emailed me 2 days ago, I am just now replying. I am not happy with that, so that's something I'm focusing on a lot currently while trying to get the content up. So, but if you do need anything, email. And there are some things. What do we say? You always go for the low-hanging fruit, right? You look at the exam, you find the easier test questions, you answer them first. If I can answer the email immediately, I do a very short answer. But if it needs any more detail, that's where I'm a little bit more backlogged than normal. All right, so we're in section 4.3 in our lovely textbook, and we're looking at division of polynomials. And so what we're going to end up with, and the book kind of says, hey, if I divide something, I have a dividend and a divisor. If I do this type of division, this is what I have. And this was made out of something. Particularly, the dividend comes that if I were to take the divisor and multiply it by the quotient, and add the remainder over the divisor. I never liked these words. I had a hard time figuring which was the dividend and which was the divisor. I think the divisor is the one I know the most now, and I've been able to say divisor easily. Dividend never stuck. But the pattern that comes out of this has always kind of worked for me. And what happens is if I start with the division, well, that gives me if I start with the answer to the division. If I start with the dividend, it's the divisor times the quotient plus the remainder. And I need to fix one thing here. And this is what happens when you're trying to, let me erase, I have an extra term here, so I'm going to erase this quotient. I should have derived it, but yeah, we'll get there, because I'm going to turn this into variables shortly, and the variables are the important part. There. So the dividend equals the divisor plus the remainder. This is why I needed that cup of coffee. This first one's right. The dividend equals the divisor, quotient, remainder. It's my second one. the one where I want to do the division up top. Here's my eraser. There we go. That was the bit I wanted to erase. So let me just erase this. And I'm going to do it in variable terms. And this is why I hate these words. I see them as variables. And the variables I see in my head are the thing upstairs and the thing downstairs. Okay, let me get back to my pen. Alright, so I'm going to put it in this format because I actually like this format, and I'm going to give an example now. If I do some division, I get an answer and a remainder, and that remainder mathematically I can add on to the end of it. So if I do 15 divided by 4. And I'll do it as a long division here. And this is where I'll see it as the pattern. I have the upstairs. 4 goes into 15 3 times. And I have a remainder of 3. So 3, I'm going to use this format. There's my quotient, 3, plus my remainder over my quotient. And mathematically, that is what this represents. And so for me, I see the quotient as the result of this division and the remainder out here. And when I was in school, we were always taught the remainder becomes a fraction. The remainder becomes a fraction where this is the denominator. This is the denominator. If you've had me in another math, or you'll see I tend to, and so I'm going to put these into Jeff words now. A division becomes the answer plus the remainder over the downstairs. All right, so answer plus remainder plus downstairs. Well, for polynomials, this comes into what we're going to call our kind of our remainder format. So I'm going to write it in the very ugly general form, but this at least has some meaning for us. So I'm going to have some polynomial I can make out of another polynomial times, and we're going to use q because whenever we do divisions, q comes up because of that quotient, plus a remainder. And this says I can make any polynomial out of other polynomials. But I do have some restrictions. The degree of my d of x is greater than 0, and my degree of d of x is greater than the degree is less than the degree of f of x. And what is nice about these polynomials is that they're unique. And uniqueness in mathematics means there's only one answer that does this. And so everything we do in division lets us build these. Now, most of the time, we like our remainders to equal 0. And the remainder is going to be a thing that's going to help us. A lot of the work that we want to do is we want to find these 2 bits of a larger polynomial of some greater degree polynomial. And so we're going to use our division algorithms to get there. So what this lets us do is try to pull apart things and look at the pieces. So I'm going to do what we did before, which was a long division. Hopefully I will have enough room, and we're going to look at the pieces. So if I want to find one with a gap, because I said I was going to start with a gap, and I had it selected, and I went back a page to pull up that definition, and I lost my gap. There we go, that's why those pages are sticking together. So let's find a gap. Alright, so I'm going to look at 3x to the 4th minus 2x squared minus 5 over 3x squared minus 5. Now my goal is to take this division and get something where I have the quotient and a remainder. And if I put it all together, the quotient times 3x minus 5 plus the remainder over 3x squared minus 5 is going to equal the upstairs. So we'll look at all the pieces in this and continue to use our algorithm within our new rule set. But notice, I said we treated the powers of x as if they were placeholders. So when we do our division here, on the outside, I don't have to worry about the place, but on the inside, I need to keep track of the powers in the polynomial I don't have. 2x squared plus... So notice in my dividend, in my upstairs, up here, I'm missing the third power of x, and I'm missing the first power of x. When I need to do my division, I need them. Now for here, some people write it in, some people don't. What's important is because we do our subtractions here in columns, that we have a column for each place. We still start by looking at the leading terms. So my leading term, and I'm going to alternate down my color palette as I do each term, just so I can focus on each term. So what do I have after pink? I'm going to have a yellow. So there's my leading term at this point in time. So I'm going to do 3x to the 4th over 3x squared. Well, the 3's cancel, and I get x squared upstairs. So for this to work, I need a single x squared. I'm going to multiply that into here. So x squared goes into, when I multiply 3x squared by x squared, I get 3x to the 4th minus 5x squared. Right? If I multiply that to this term and to this term, I get these two terms. To subtract, I'm going to change signs. So that's going to become negative. That's going to become positive. If I've done this first step right, using these leading terms, these will always cancel. So I get 0x to the fourth, 0x cubed, and a positive 5x squared, and a negative 2x squared gives me 3x squared. Bring down the 0x, and I bring down the minus 5. My new leading term is here. I'm now repeating what I've done before, and this leading term. So 3x squared over 3x squared is 1. So I'll multiply by positive 1, and I'll multiply this by positive 1. So I get 3x squared minus 5. I go to subtract. So I change my signs. If I've done this portion right, the leading terms, the leading part should cancel out. I get a 0. And what's nice, this gives me a 0, and I get a remainder of 0. And so this is my answer. And I will transfer back to the pane. Now what this is telling me is that these two things multiplied by each other should give me what's upstairs. Well, let's verify that. Let's make sure our division algorithm is working. So I get, I'll write it on the bottom and then scroll up, x squared plus 1 was my answer. Division is telling me if I multiply that by 3x squared minus 5, I should get all of this back. Right, and I'll put a question mark over it because that's what we're checking right now. So we'll scroll and put that up top. And so here we're verifying our division. So I'm going to use FOIL, my first times my first. So 3x squared times x squared is 3x to the fourth. I'm going to use my outers. So x squared minus 5 times minus 5 is minus 5x squared. I'm going to use my inners. So 1 times 3x squared is positive 3x squared. And I'm going to use my lasts. And negative 5 times 1 is negative 5. I collect like terms, so I only have one term to the fourth power. These combine to give me negative 2x squared, and this stays negative 5. And so, yep, this was true. My algorithm for long division works. Notice the focusing on leading terms. Okay, I'm going to continue to do examples that use division with remainders, and then we're going to check the answer so that we can see that our division algorithm is going to work. So what I'm going to do is I'm going to use examples to say, hey, sorry for the scrolling, if I divide, I get this answer. And if I multiply, I get back to what I started with. So let's put these examples out. So dividend divisor equals quotient plus remainder over divisor. That's if I'm doing the dividing. If I'm doing the multiplying to check, that is what my check would be. So notice what I'm doing is if I take this equation and I multiply both sides by the divisor, I get the divisor times the quotient, and then they cancel out here to give the remainder. We could say the top way is what we get when we do the division, and the back way is what we do when we check our division. But remember, mathematics are talking about reversible process. And so this is a valid statement about things we might see. And what happens when the remainder of 0 has some important implications for what we see for larger polynomials. So we're going to keep these two forms, which are so horribly wrote in the first 2 minutes, in mind, and we're going to do some other divisions. So, and we're going to check them. We'll probably scroll up and down to this after I do each one. I need most of a page to do a division, so you're going to see some scrolling up and down, but we're going to continue here. And I'm going to focus on that algorithm, which is look at the leading terms, do the division of the leading terms, multiply, subtract, you get a new leading term, repeat. So I'm going to divide 5x cubed minus 4x squared plus 7x minus 2, and I'm still going to divide it by x squared plus 1. X, that's an x, squared plus 1. So I'm going to set up my long division, about here-ish. So x squared plus 1 going into 5x cubed minus 4x squared plus 7x minus 2. Now I'm going to check right now. I've got a 3, a 2, a 1, and a 0. So that works its way down, which is what I want to see. I want to see descending powers of x. So I start with my first leading term and the leading term of my divisor. So 5x cubed divided by x squared is equal to 5x. So I will put 5x up here. And now I need to multiply 5x through my divisor. So 5x times x squared is 5x cubed. 5x times 1 is 5x. Notice the gap. Right? I do not have anything in the x squared term. Your book, I think, writes in 0x squared. I leave a gap, and I keep my sign over here. Again, our goal is lining up by powers of x. So if I look up from anything here, I should see the same power of x. And so I want to subtract these, so I'm going to change the signs, right? Because subtraction is a change of sign. And so this becomes negative also. If I've done my job right, the leading terms should cancel. Right? 5x cubed and a negative 5x cubed is 0. But notice, I'm now going to have a negative 4x squared. And this is now negative. So minus 2x. Oh, wait, it's not minus 2x, it's plus 2x. This is a negative 5, and that's a positive 7, plus 2x. I'm looking at it going, yeah, this is still positive. And so this larger positive and this negative is 2x. Pretty sure someone would have thrown an eraser at me in the class. All right, so now I have a new leading term. So I'm going to underline my new leading term. It's negative 4x squared. So negative 4x squared divided by the leading term of this, which is x squared. The x squares cancel, and I get negative 4. So my negative 4 comes up here, and I'm going to multiply it back through. So I get negative 4x squared minus 4 as it comes through each term. I'm going to subtract. So these signs change. This becomes positive. This becomes positive. And for completeness, I'll bring down the negative 2. I'll bring everything down. If I did my job right, notice my repetition, because this is a repeating algorithm. We repeat steps. The negative 4x squared and my leading term from my multiplication should be a positive 4x squared. When I do my subtraction, they should cancel. The 2x comes down, plus 2, and that's my remainder. So I would write my answer as 5x minus 4 plus 2x plus 2 over x squared plus 1. Well, where's this coming from? Why am I doing the remainder like this? I told you I'd scroll up a bit. All right, it's my quotient plus my remainder over the divisor. My quotient, which I found here, plus my remainder over the divisor. All right, well, let's check this. And this is where all our multiplication and factoring came through. So if I'm going to check, I'm going to do the same thing I did before, and I'll write what we should see and double check it. So this 5x minus 4 plus 2x plus 2 over x squared plus 1 as a factor times x squared plus 1 should equal, put our question mark here because we're checking, 5x cubed minus 4x squared plus 7x minus 2. I should get back to where I started if I reverse what I did. If I divided, multiplying should get me where I started. We're just doing it in this particular thing with polynomials. Well, when I multiply, I've got to multiply this towards the first term, this towards the second term, and this towards the last term. And this, I'm going to take the whole thing. I'm going to distribute the whole at once. So I'm going to bring this whole thing over next to 5x. So I get 5x times x squared plus 1. This whole thing is coming over next to 5x. Next, this whole thing is going next to negative 4. So this whole thing multiplies next to negative 4. Whole thing comes through. So what we have in the parentheses, we can imagine is a portable number, right? That parentheses is like a bucket, and we carry it around as one portable number. And so we pick the whole thing up and we multiply it through each term coming across. And this term times the whole thing. So I have distributed across 3 terms. Normally we've been doing 2 terms for distribution, but I've now distributed across 3 terms. This sets me up with 1, 2, 3 more multiplications I need to do. So 5x times x squared is 5x cubed. And 5x times 1 is 5x. Negative 4 times x squared is negative 4x squared. Negative 4 times 1 is negative 4. But here comes the fun part. Notice this is the same thing that's in the denominator. So they're going to cancel, leaving me with the 2x plus 2 upstairs. And that's why the remainder hangs out like that, and we have the remainder coming across. And this should start looking like the other parts. And so if I collect like terms, I have for my cubes, I only have one thing cubed. So I'll put 5x cubed out front. For my squares, I only have one thing squared. For my first power of x's, I have 7 of them. And for my constants, I have negative 2. And look, this was true. And so our division algorithm, our way of writing divisions, has a way of letting us see which parts come together and pull back together. It becomes reversible. And so our remainder pops out of it. Well, we can use this to look at how multiplications work together. So one of the things the book will ask you, it'll say, if I have the parts, if I have x cubed minus 8x squared plus 15x minus 6 over x minus 2, and I know that answer, I get x squared minus 6x plus 3. Well, that's telling me that x minus 2 times x squared minus 6x plus 3 is equal to, so let's see, if this was an equation and I wanted to get rid of the denominator, I multiply the left-hand side by the denominator, it'll cancel, and I multiply the right-hand side by the denominator, I get this. So if it cancels over here, I get what's upstairs. Now, this might seem a little trivial, right? That the reversing a division tells us what our multiplication is. But notice, if this was the polynomial I had, and I wanted to simplify it into linear or quadratics, things I've already done, the goal is trying to find something that divides. Now, out of this comes one of the more useful things, which is called the remainder theorem. And we're going to come back to the remainder theorem when we try to find roots. So if I have some polynomial, so here is the remainder theorem, and this is going to help us find roots later on when I have an idea of what a number might, what a root might be, or what a factor might be. I can use the remainder theorem to check if I'm right. and this can help really quickly go through. What we're going to find is that when we have something to the 8th or 9th power, and we need to break it down by finding roots, the remainder theorem will help us find the roots quickly. So let's start with the remainder theorem. I'm going to have a polynomial which I'm going to call f of x because I like. So I have a polynomial function f of x, and I don't want to use I, right? So the polynomial f of x is divided by x minus k. Watch the sign here. Then the remainder is the function of k. Now I'm going to point to some caveats here, or some things we have to pay attention to, because this is really going to help us. This x is to no power. It's to the first power. It's x minus k. So this is a linear factor. Here's the word I'm going to, x minus k would be a linear factor. And if I put the value of k back into the function, I get the remainder. All right, well, let's show this in action and verify the answer. So, let me go with the one that's going to be the easier division. So I'm going to have a polynomial, f of x equals 5x squared minus 3x plus 1. And I'm going to divide it by x minus 1. But all I want right now is the remainder. So I'm going to use the remainder theorem. So I look, hey, this is to the first power, and so my k is positive 1, right? Notice the sign here. So I'm going to, in this form, k is equal to positive 1. Please note, it's negative in my theorem. So the number I'm pulling out is the 1. So I want to find out what f of 1 is. So I'll put 1 in for wherever I see x. And so 5 minus 3 plus 1, or 3. And so my remainder would be 3. Do you believe it? Do you trust me enough to believe it? You shouldn't. It's true. I mean, it really is true. But this is something that, for how useful it is, you're going to want to believe it by seeing it a little more. So let's do this. Let's do this division and see if we get a remainder of 3. So I'm going to change colors here for the division. I'll go to my bright green. X minus 1. Going to divide into 5x squared minus 3x plus 1. Thanks, Billy. I'm going to check. Do I need the exponents? The exponents need to be kept in line. And for the remainder theorem, all it's telling me is the remainder. And in this case, it's just a number. Oh, you mean, I see exactly what you mean. That's squared.
Yes. Yeah. Yes, you do need to keep them. I knew 1 squared was 1, so I kind of skipped it going through. That was more. And you're talking about where I wrote there. Is that correct, Lilika? Did that answer what you had there? Through here, I'll change my colors. I think this is what was meant, was do I need to put the exponents in? And yes, when substituting in, we keep the exponents in place. I picked the one with the 1. Remember when I said when you test things or you're looking for an easy thing, 1s and 0s are nice? Well, so I picked the one with the 1. And of course I forgot the square because 1 squared is 1. So, bad me. Thank you for pointing it out. Well, look, we're going to verify it here. So I made sure my exponents go in descending order. And I focus on my leading terms. So 5x squared divided by x is going to give me 5x. So my first part is 5x. And I'm going to multiply this to each term here. So 5x gives me 5x squared minus 5x. Okay, boom, 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 boom. I'm going to change my signs to subtract. So this becomes negative, that becomes positive. If I did my job right, these leading terms should cancel out. And this becomes 2x plus 1. On this one, no, we don't have to add a higher order power. We can start with the highest one and go down. We never need to add. They're technically there. There's 0x cubed, there's 0x to the 4th, they're there. But we start with the highest and go down. We only put things that are missing between the highest and the lowest. The answer is what Keon asked. Keon asked, do we need to add the 0x cubed? In this case, no. This is only a degree 2, and I'm using a degree 2 because it shows the remainder 0 quickly. And I think I'll do a longer one afterwards of it also. So this is my new leading term. And when I divide these cancel, leaving 2. And it's a positive 2. So I'll multiply my 2 back. 2x minus 2. I'll change my signs. And if I did my job right, these terms cancel out. Look! My remainder's 3. I told me it was going to be 3. It's 3. So the remainder theorem seems to work. And I guess if I wanted to write this in proper form, it would look like that. And so the remainder theorem is useful. I'm going to look at another remainder theorem, and I'm going to go to a higher order to show spacing. I'm going to use the hardest one I have. And that should fill the last of the space. I'm sorry about the scroll bars on this. I think one of the things I'm going to do in the future is trying to get a way of showing 3 blackboards up at once. I wish we had conference software where you could choose your own windows. But in an ideal world, we would be doing ideal things. Alright, so the function I want to look at here is negative x to the 4th plus 4x cubed minus x plus 3. And I'm going to divide it by, we'll divide f of x by x minus 3. So to do that, I'm going to first see if it has a remainder. So does this have a remainder? So I'm going to use the remainder theorem. Now the remainder theorem says this is x minus k. So my k is going to be a positive 3. Kind of have to reverse the sign here. And reversing the sign is the thing that comes up in divisions, especially when we do the technique called synthetic division. So I will want to find this. So I'm going to put 3 in, and I'm going to remember my powers. I hope I remember my powers. Alright, so let's see. Did I put 3 in? So negative 3 to the 4th, 3 to the 4th, 4 times 3 to the 4th, 4 times 3 to the 3rd. Said it wrong. Minus 3 plus 3. Alright, I'm going to punch this in the calculator. And in fact, having your calculators handy for these and using your parentheses will help. So negative parentheses 3 to the 4th plus 4 times 3 cubed minus 3 plus 3, and I get 27. So if I were to divide this function by x minus 3, I would get 27. Now I'm going to do the double check on this. I'm going to take x minus 3, and I'm going to divide it into this. But nope, I have my missing x squared in there. Alright, so my leading term, I need a negative x cubed. I'm going to do this one a little quick because I want to talk a little bit more about the remainder theorem. So negative x cubed times positive x is negative x fourth minus 3x cubed. I will change my signs. Again, if I did my job right, that leading term goes. And my new leading term is 7x cubed, which I'm going to divide by x, positive 7x squared. Alright? And I'm going to pull down all of this to do my next subtraction. I'll do all my subtractions on one line. I have a tendency to do them in columns, but I'll pull everything down for you. Alright, so I'm going to multiply the 7x back through this. So 7x squared times x is 7x cubed. 7x squared times negative 3 is negative 21 x squared. I'm going to subtract. So I changed my signs. If I did this right, this leading term will cancel out. And I get 21x squared minus x plus 3. Well, to get 21x squared, if I did this is my new leading term, if I divide these, I get a positive 21x. So I'm going to multiply it back through. And so 21x gives me 21x squared minus 63x. I'm going to change my signs. And if I did things right, these first terms should cancel. And I get 62x. I'm trying to see if I got a sign error in here. If I did, we'll see how to fix it. Because making mistakes are good. Oh, I'm a big believer in making mistakes and fixing them as we go. And long division is one of those things where corrections are neat. Notice how I keep saying if I did this right, this leading term should cancel. I have done it wrong. And the leading term hasn't canceled, and I've used it as a check. So there are places where you can make mistakes. And so let's make sure I did 21, negative 63, 62. And I'm going to pull down the 3. Yeah, I'm not going to get 27 back out of this. So I made a sign error. So let's just double check my sign errors. Negative x is negative x fourth. There it was. My sign error was my very first thing up here. We kind of knew I had a sign error when this got bigger, but I didn't see it right off the bat. And again, these are good things to double check. And the remainder theorem is a beautiful way of double checking your divisions, which is the point I wanted to get to. So I like that. Try to tell teachers that making mistakes are a good thing to do so that you can figure out how to find mistakes. Notice, I knew what my remainder had to be, so I had to double check for myself. When this number got big, I saw I wasn't getting towards it and had a sign error. My sign error was actually here. When I multiplied negative x cubed times negative 3, it should have become a positive 3x. Instead of doing this, this should have been a smaller number coming through. I had that feeling. I commented on it. I said, oh, let's do it and see what happens. Oh, my eraser is not erasing one. Let's get a better eraser. I like this program for this alone. The erasers actually look like erasers. And I'll also say that this is the beauty of the remainder theorem. It will let you check your work relatively quickly. Alright, so I was right with my leading term that I needed a negative x cubed. When I did this first multiplication, this should be negative x to the fourth plus 3x cubed. I had put negative x cubed in there, and that made my mistake. So when I change my signs, this becomes positive, and this becomes negative. If I did my job right completely, the first term should cancel. And this subtraction gives me x cubed, not 7x cubed. And that's where my numbers got too big. Now I'll bring down the rest of it. And I'll look at my leading term. X divided by x cubed divided by x is a positive x squared. So I will now multiply this back through. I get x cubed minus 3x squared. I will change my signs. If I've done my job right, the leading terms cancel. And here I'll have 3x squared, and I'll bring down the rest. This is my new leading term. X, 3x squared. So 3x squared divided by x is positive 3x. So I'm going to multiply this back across. 3x times x is 3x squared. 3x times negative 3 is minus 9x. I will change my signs.
Change my signs. If I did my job right, the leading terms cancel. This gives me 8x plus 3. My new leading term is 8x. So 8x divided by 8 is positive 8. 8 times x is 8x. 8 times negative 3 is minus 24. I change my signs. Change my signs. If I did my job right, the first terms cancel, and I'm left with a remainder of 27, and it works. I try not to work out problems ahead of time so I can make common mistakes and show you how to correct them. It's hard because when you do more and more of these problems, it's harder to make a mistake. But I have found making a mistake and correcting a mistake is actually valuable for teaching. When I tutor, we look for where mistakes are, and you start seeing common things you do. And unless you do loads and loads of problems, you don't see all those kind of gotchas. And so when I do things on the board or here, I have picked problems, I picked the answers. I've sometimes worked out some of the more complex ones, but I try not to do it from notes so that I can do what I just did there. But I'm a human being. It's still really embarrassing when I make a mistake, even though I know I want to periodically. And I think in long division, yes, the x cubed on the very front is x fourth. Thank you. Thanks, Billy. And if I did my job right, that leading term should cancel. And I liked this mistake. It was a sign error, and sign errors are the common mistake. And I knew it was there. So as I was doing each step, I was trying to find it. Notice how the remainder theorem told me I made a mistake. This is where one of its most usefulness comes into place. So I'm still embarrassed. I'm human. This is up on YouTube now. Everyone can see, Professor Thompson making a mistake. But it's also very important that we look for where the mistakes are and how they happen. And sign errors will be the mistakes in long division. And when we switch over to synthetic division, keeping track of your signs are just paramount. And so you got to kind of look for sign errors, look for sign errors, look for sign errors. And the remainder theorem is a great way to check. There's also something really neat that the remainder theorem is going to tell us. And I got to the end of this page, so let me save this and I'll start a new page. Remainders tell us about factors. If you divide something and it goes in evenly, what is the remainder? Okay. So if I divide something and it goes in evenly, what is the remainder? And that's really where the usefulness of the remainder theorem is going to jump out and kind of hit us, is that if I have perfect factors, there are no remainders. I'll show you what I mean with numbers. Then I'll hint at where this is going. So if I did 15 divided by 4 earlier to show that if I do this division out, it goes in 3 times with a remainder of 3. But if I were to divide 12 by 4,
goes in 3 times with a remainder of 0. 0 remainders shows we have perfect factors. And let's show this in reverse. And I'm just going to use a quadratic, though I could do more, x minus 3 and so on. I could make this a larger and larger polynomial by adding more factors, but let's just look at the quadratic. So my firsts are x squared, my outers are 5x, my inners is negative 2x, and my lasts is negative 10. And so I have a polynomial that I know has perfect factors. Well, let's look at the remainder theorem. Let's say if f of x is x squared plus 3x minus 10, and I'm going to divide it by x minus 2, do I have a remainder? So I'm going to put f of 2 in. And so I get 4 plus 6 minus 10, 10 minus 10, or 0. If I were to divide this by x minus 2, there would be no remainder. It's a factor that made this. But let's say I was to divide f of x by x minus 5. So I'm going to use the remainder theorem. Oops, not minus 5. Right? Nope. My k is equal to positive 5. I'm going to do minus 5. 5 squared plus 3 times 5 minus 10. Kept slipping into doing the actual one, right? But if x minus 5, right, my remainder theorem says x minus k. So my k is positive 5. So 25 plus 15 minus 10. Well, 25 plus 15 is 40, and this is 30. It has a remainder. This is not a factor. And of course, x plus 5 is the other factor. The remainder theorem will help us check our long divisions. It's also going to help us find things that are factors. Notice this was cubic. It was built, or cubic, quadratic. It was built off of 2 factors. So if I have an x to the nth, I have a possibility of n factors. The remainder theorem is going to really help us weed through all the possibilities quickly. So I might not be able to give you the exact answer, but I can give you a possible one. And the possible one and the remainder theorem go hand in hand. But for now, we want to practice division. Now, we have done long division of polynomials. And that works no matter the divisor. It can be x squared plus 1. It can be x cubed minus 3x plus 4. It could be x minus 1. And the divisor is the thing that we're dividing by, right? We divide by. Because a lot of what we're doing is going to be looking for factors and roots, and they will be the things that are the x minus k's, there's going to be something called synthetic division. That only works for x minus 1, x plus 1. It only works for things x minus 3, x plus 3 halves, okay? These will all work because x is to the first power. And we're going to do synthetic division next time. Our game will be finding roots, and roots are the linear factors. Go hand in hand. Roots, zeros, and solutions are related to the linear factors. We're learning to divide so we can get there. And so synthetic division goes a little bit more quickly than the division, long division. It's faster. It has some sign issues, so expect me to make at least 3 mistakes. I am sorry today. I really need a cup of coffee or something. I've been saying things backwards a little bit here, and it's odd. I was like reading this stuff and organizing my notes a little bit more than normal. It might have been pressure to try to get this perfect, but I am happy I made that mistake there. I'm going to keep convincing myself of that because it shows the importance of signs and where we want to find sign errors. And thank you for pointing out where I put the power wrong. I was really trying to emphasize the leading term go away bit this time around. Maybe on my next ones I'll emphasize the check your sign, because those are the common places where you can catch yourself. I have homework for chapters 1 through 3 up. It'll be due end of next week. The exams are up there. I've shown everything on Pearson. I'm going to continue recording example videos for the review material in chapter 3. And I'm going to be doing a lot of examples of the long division and synthetic division so that we can see different examples. This is one of those things where I still find interesting patterns in certain types of problems when I do a type of problem set, and I think I'll put up a video or start the next lecture with an example of how we can put a variable in a different place and we can get some information out of these things. That was something I learned teaching this stuff a few years ago, which I didn't think would fall out of long division. And this is one of those things where you have to do a bunch of them to see all the variances that can happen and how useful it is. So I want to leave it at that. If you have any questions, email me. And if you need anything, again, I pushed the dates out on exam 1 because Pearson's having some odd problems. But I would try to get exam 1, exam 2, the chapter 3 exam. I would try to get it. If you're comfortable with the material and you're ready for it, take the exam. If you still need some things, keep asking me questions. I am putting the word problems up on the review bit because most of my questions were with review. I had someone ask me about completing the square. I'm going to also do a couple completing the square problems. I did 2 of them, but I think the audio was off. So I will work on making sure there's some examples up for that. And then come tomorrow, I think my major focus is going to be putting up a lot of examples of division. And what we can do with polynomials. So that said, be safe, be well, have a great one, and email me if you need anything.